Often while working with different kind of data sets, we come across different variables. So we may be dealing with variables which are purely numerical in nature, and then we may also be dealing with variables which are categorical in nature. When we're dealing with two numerical variables, we have a de facto choice that's known as the Pearson's correlation, which is a measure of linear association between the numerical variables. Now the question is, do we have something equivalent for the categorical variables? And the answer to this question is that yes, we have an alternative that's known as the Cramer's V. Now what is Cramer's V? Let's understand this. So Cramer's V is calculated as the square root of the chi-square divided by n multiplied by the minimum of r minus 1 and c minus 1. Now, this is not a very complicated formula, but let's understand each of these terms. We have a chi-square test statistic here. We have the number of observations. We have number of rows and number of columns. If this looks a bit daunting, let's give it a little more time and you'll be able to understand what all these terms are. In fact, we've done a separate tutorial on this topic that's known as the chi-square test of independence. You may refer to that. But for the time being, to calculate this statistic, let's take an example and understand this step by step. So let's say we are trying to check the dependence of two variables, and the problem statement goes like this. A company owns two gaming apps, P1 and P2. It is trying to determine if education has a significant impact on the type of app that users prefer to use, specifically differentiating between individuals with a technical, tech, and non-technical or non-tech background. Using the data provided, we can conduct a test of hypothesis. Now, in this case, we are not going to perform the chi-square test because we've already covered that at length in a separate tutorial, but we will just see how the data looks like and under what circumstances we can apply this approach. So here is how our data looks like. We have a column called, let's say, platform or the app, and we have the education. So P1 and P2 are these two categories in the column B, and education, which is tech and non-tech, are two other categories. You can imagine you could be dealing with a large data set which would have many more variables and variables of different nature, but for the time being, we are just concentrating on two variables which are both categorical in nature. If you're familiar with how to deal with two categorical variables, the first thing you want to populate is a contingency table like this. So this kind of summarizes the data that we had in the Excel sheet. We have a total of 60 rows or observations in the data, of which 27 belong to the platform P1 or app P1 and 33 belong to P2. And this is the breakup of tech and non-tech. So for example, when you break that 27 for tech and non-tech backgrounds, the numbers are 21 and 6. Similarly, when you break 33 into tech and non-tech, the numbers are 15 and 18. So you just have a 2x2 contingency table. And we also have populated these margins, which are 27 and 33 and 24 and 36, both leading to a total of 60. Now, we will not do the calculation of chi-square statistic here, as we've already covered in a separate tutorial mentioned earlier, but let's try to use the values that we computed earlier into the formula. So once again, here's how the numbers will populate. The chi-square statistic, if you calculate, would turn out to be 6.46. Total number of observations we can see in the table are 60. Number of rows are 2 and number of columns are 2. You don't count the margins or the total rows for this. You only count the core observations, the frequencies that you have in the table. And now if you bring this formula where you plug these values and you do the calculations, you'll realize the Cramer's V is computed to be 0.328. Now, is there a way that we can interpret Cramer's V? The whole reason why we came here is because probably we want something parallel to the Pearson's correlation coefficient. One of the things that makes Pearson's correlation coefficient very popular is the fact that it always lies between the values of -1 to 1. It's a range-bound thing, and which makes the evaluation and interpretation very straightforward. Luckily, we have something similar for Cramer's V as well. And what is that? So if you look at the value of 0.328, we should be able to assess, is it a strong association or a weak association? Now, Cramer's V is always going to be between 0 and 1. And here is the guideline for interpretation. If we have a value which is 0, it indicates no association. If we have a value that's greater than 0 but less than 0.1, less than or equal to 0.1, it indicates a weak association. If we have a value greater than 0.1 but less than or equal to 0.3, it indicates a moderate association, and a value greater than 0.3 but less than or equal to 0.5 is a strong association. And this is the case where our computed value falls, because the value that we computed is approximately 0.33, which indicates a strong association. If you refer back to the tutorial on chi-square contingency test, you'd realize there the hypothesis also concluded that there is a dependence between the two variables. So if you have been following the sequence of tutorials that we have published, we've talked about Pearson's correlations, we've talked about Spearman's rank correlation, we've talked about point biserial correlation, and now we are talking about Cramer's V. Keep learning. Thank you.